So the topic of today is del Pezzo surfaces. So X is a del Pezzo surface if it's a smooth surface with ample anti-canonical divisor. And all the theorems which we will discuss today actually work over any characteristic and even over not necessarily closed, algebraically closed fields. But some of the proofs we don't want to do too many cases or use too advanced methods, so some of the proofs will be, we will assume that K is algebraically closed and has characteristic 0 just to make it shorter. And the aim of today's talk is to show that if X has degree at least 3, then the anti-canonical linear system is very ample and induces an embedding of X into some projective space. And then when X has degree 1, 2, 3, or 4, we will be more explicit and we will embed X into some projective spaces or some weighted projective spaces. Those are the main theorems, which is the aim, the purpose of today's talk. And first we will need some prerequisites.
Why don't you consider the Pezzo surface is canonical, the Pezzo surface of degree 1, 2?
Of degree 1, 2? Yeah. So if they have degree 1 or 2, the anti-canonical linear system will not be ample. We will see this later. And we will embed it into some weighted projective space. We will see this later. That's the aim. But first we need some prerequisites. So if you remember, prerequisites. If you remember last time, Prokhorov defined the ring Ri. If we have X and we have some line bundle L to be the vector space of global sections of L to the power of I. And he also defined the graded ring. This graded ring for any line bundle L. So L is a line bundle. And then we have the first important property. It says that if R1 generates the whole graded ring, so if the first component of our graded ring generates the whole graded ring, then L is very ample. And this is because we have a surjection. So if R1 has, say, n generators, then we have a surjection from the symmetric power of K of x1, xn, where n is the number of generators of R1. We have a surjection to the whole graded ring.
So you assume that L is n?
No. We assume that R1 generates the whole ring. Yeah. We assume we assume that L is n. L is ample. Yes, and L is ample. Because when L is ample, then X is isomorphic to Proch of Rx L. And a slightly more complicated case, R2, which we also need to discuss, say that R less than or equal to alpha. So this is just direct sum of I equal to 0 to alpha of R I x L. So if R less than or equal to alpha generates the whole ring, generates R, and if we know that L is ample, then how can we use a similar construction to embed X into some weighted projective space?
I think it's from 0.
It doesn't really matter, but so this is some construction which we will use later, which is somewhat important. So the idea here is that first consider R1 and say that it's generated by some elements A1, no, let's say A11, A1, S1. And then let's consider R2 and say that it's generated by some elements which comes from taking products of elements in R1. And we need additional elements R21, A2, S1 elements to generate the whole S2, the whole second component of the graded ring R. And we continue like this onto R alpha. And then R alpha is generated by some products of elements from the previous components plus additional elements, A alpha 1, A alpha 1, A alpha is alpha. Alpha 1, tack. Okay, and we want to use a similar construction, so we want to have some surjection from some graded algebra to our graded algebra R, which gives an embedding of X into some weighted projective space.
Now the question, if everybody knows what is a weighted projective space.
So Prokhorov defined it last time
Okay.
as a quotient, and I think he also defined it as graded Hodge.
Okay.
Yes, so we have a certain graded Hodge which corresponds to some weighted projective space such that we can construct a surjection from that graded algebra to our graded algebra R. So it will be some weighted projective space where we will need some number of ones. Then we will need some number of twos.
So now that it's in your notation is S1.
Yes, yes. So that's the I wanted to ask it, but okay. And then this will be S2 and so on. And here we will have S alpha alphas.
Sorry.
So I'm not. So this projective space, weighted projective space, is the same as the Hodge of the graded algebra, which is generated by S1 elements of degree 1, S2 elements of degree 2, and so on. And so by construction, some graded algebra here, we can call it R, I don't know, S1, S2, S alpha. And we have a surjection from this graded algebra to this graded algebra by construction. So this means that in this case, when the first alpha components of our graded algebra R generates the whole graded algebra, then we can embed X into this weighted projective space. Okay, we will see some examples later. This is just important. Then I want to erase here because I want to put more prerequisites here. We also need some general formulas to be able to compute intersections and cohomology and this stuff. So let C be a curve or divisor on some surface S. Then we define the Euler characteristic of C to be equal to the Euler characteristic of the divisor associated, the line bundle associated to this divisor, which is equal to the alternating sum of cohomologies. So we will have H0 of this line bundle. Let's just denote it by C instead of OS of C minus H1 plus H2. And S, the smoothness dimension 2, so we don't need to consider any higher cohomologies. That's the Euler characteristic. Then we need two important formulas. The first formula is Riemann-Roch for surfaces, which states that the Euler characteristic of C is equal to the Euler characteristic of 0. So 0 here means 0 as a divisor, and 0 as a divisor, that's just the structure sheaf. So this is the Euler characteristic of the structure sheaf of S, plus a half times the curve intersection number between the curve C, and it's a plus or minus the canonical divisor here. I always forget. Minus the canonical divisor of the surface. That's Riemann-Roch for surfaces. And then a junction formula is also important. Junction formula. This one says that 2 times the arithmetic genus minus 2 is equal to C intersected with, and here it's the opposite, so here it's plus. Okay, so I think it's not so hard to obtain these two formulas from each other, but they are each important and will just be applied a lot of times. So let's do an example. So if S is P2 and C is a curve of degree 3, what will be the arithmetic genus? So maybe I should write that S is equal to P2. C has, it's some cubic curve, has degree 3. Using this formula.
1.
Yes. This is 0. And this, notice that C can be any cubic curve. So it can also be singular. It can be a smooth cubic curve, a cuspidal cubic curve, a nodal cubic curve. So when we obtain singularities, the geometric genus drops by 1, but the arithmetic genus, this is the arithmetic genus, it stays the same. That's important. Then finally, prerequisites, we need some facts about line bundles and curves. So facts about line bundles on curves C with arithmetic genus equal to 1. So C can be either a smooth cubic curve, a cuspidal or nodal cubic curve. Then if, depending on the degree of L, we will have different properties of the line bundle. Property so when the degree will be at least something, then the first cohomology of the line bundle will vanish. When the degree will be at least something, then the linear system associated to the line bundle will be free. And when the degree will be at least something, then this linear system will be, or the line bundle, so to say, will be very ample. So these are just some facts which we don't want to go into too much detail, and we will use this to prove the same, similar, almost the same, for del Pezzo surfaces. And the reason we focus so much on curves with arithmetic genus 1 is that a general member of the anti-canonical linear system on a del Pezzo surface is a curve of genus 1. So we are using these curves to embed our surfaces into some projective spaces. So these curves are very important. So what should be the minimal degree to ensure that first cohomology vanishes? So how can we compute the first cohomology? We can compute it using a Z duality. So by Z duality, this physical homology will be equal to what? Yeah, we can also use Riemann rock. We can also use Riemann rock. We can do this in a lot of ways. We just need a number here.
One.
Yes. What is your argument?
My third duality.
Yes. So this is equal to
H0 of LDO.
Yes. And a line bundle with negative degree can't have any global sections. Maybe I should write it H0 of.
А если любая кривая произвольного рода, то что здесь должно стоять? If any genus by sexuality, по ответственности. Какое бы число там мы поставили, если бы произвольный был род? Давайте тогда уж до конца выясним этот вопрос. А? Ну, почти, да, только чуть-чуть. Как степень канонического класса какая? 2g минус 2. Здесь это было бы 0, да? Значит, 2g минус 1. 2g минус 2 плюс 1. Потому что у самого там бывает. То есть, да. Значит, здесь было бы стояло 2g минус 1. Да? Давайте, надень вот здесь.
Okay.
Вот здесь вот сбоку, вот просто напиши вот здесь. Для произвольного рода.
Okay.
Да.
It's for smooth.
No, we have arithmetic genus.
It's arithmetic genus, поэтому это не важно.
So here we will have, okay, I can't do this computation. Maybe some people can do the computation on paper for me. What?
Degree.
Here?
No, just not
Degree of
C, but degree.
Да. Yeah, so using this and using Z-duality, we should.
Мы уже нашли 2g минус 1.
Вообще.
Все уже поняли, мне кажется. Ну, по крайней мере, мы уже это определили.
Хорошо.
Давай, дальше. Дальше тут.
Хорошо. Okay, so for. Okay, next question. When will it be free? Base point free? And probably, not just right, it's probably better to use Riemann rock, but.
Ну вот степени 1 достаточно, чтобы быть свободным.
If it's a genus 1 curve.
Да, если кривая рода 1, что там будет, сколько там будет сечений? Одно.
Ага.
Одно сечение, и, соответственно, у него будет где-то 0 у этого сечения, поэтому он не является это. А двоечки достаточно? Ну вот, одного недостаточно, очевидно, да? Вот, а двоечки достаточно? Ну, это просто надо формулу тоже Рiemann-Rocha, сколько сечений будет у двоечки. Во-первых, в гомологии нет, поэтому все сечения можно посчитать по формуле Рiemann-Rocha, сколько их будет. На кривой рода 0, 2 сечения. Ну, дальше, конечно, там, может быть, какие-то рассуждения требуются, но, в принципе, 2 сечения.
Да.
Да. Достаточно, и будет она двулистно отображаться на проективном пино.
Да.
Ну, а теперь следующий вопрос.
Yes.
Вот это 2 достаточно, чтобы было очень обидно. Почему? Ну, вот потому что, вот если мы возьмем степень 2, то оно дает какое отображение с кривой эллиптической? Двулистное отображение в P1. Значит, оно не вкладывает ее, значит, двоечки недостаточно. Теперь осталось спросить, достаточно ли троечки. Если вот сколько сечений будет у линейного расслоения в степени 3? Ну дальше по Рiemann-Rocha. А? 3. Тогда 3 сечения. Куда отображение у нас идет? P2. Ну и мы знаем, что это на самом деле вложение в кривой степени 3. То есть вот как раз троечка здесь достаточно.
And I don't remember exactly what it should be here, but okay, I think this is exercises here. Вот так. Так, что дальше? Да, что-то еще более непонятно, где это будет. Давай сюда. Okay, so if we have a curve C with still with arithmetic genus 1, and we have L is a line bundle, then we know that the line bundle is ample. If it has degree at least, so degree of L is at least 1. Because then at least L to the power 3 will have degree at least 3, so L for sure will be ample. This means that we can consider, that it's interesting to consider the ring RCL. And then the question is, how many components do we need to generate the whole graded ring? So this will be generated by R less than or equal to alpha for some alpha, where alpha is equal to something which depends on the degree of L. So for instance, if the degree of L is equal to 3.
Are you talking now about elliptic?
Still, so this is still this case.
Okay.
So GA is equal to 1. That's the only curves other than rational curves which we are really interested in today. So alpha, if the degree of the line bundle is 3, then we know that it's already very ample. So then we know that this graded ring is already generated by the first component. But then the question is, what if the degree is equal to, or if it's at least 3? What if the degree of the line bundle is at least is equal to 2, or what if it's equal to 1?
Can you say again what did you...
So
we have degree at least 3 and then it's degree first.
Because it's very ample.
Because it's very ample.
Yes, because it's very ample and yes.
If and only if.
Yes.
There is an error from the right side.
Yes. So, but what if the degree is equal to 2 or 1? How many components of this graded ring will we need to generate the whole ring? And okay, maybe somebody can guess. We don't want to do this because actually it's a bit complicated. Maybe somebody can guess what should be here. Yeah, and here. Why? Yeah, so you can check this explicitly. You need to check it explicitly because, okay, even though L to the power of 3 is very ample, this means that this, the first 3 components here, for instance, for sure generates all the components which are divisible by 3, but we would still need to check all the components of this graded ring which are congruent to 1 or 2 modulo 3, and that is not totally obvious, but it's true, and we don't want to check this right now.
It's not difficult actually.
Yeah. Okay. These are the prerequisites, and now we will try to prove everything which we are saying, at least in characteristic 0. So the proposition, which will take multiple lemmas to prove, proposition 1, says that if we take a member of the anti-canonical linear system, then C is irreducible.
X is the surface.
Yes. So now we're going back to the real part of the talk, and throughout all of this talk, X is a smooth del Pezzo surface. And the first proposition says that if we take a general member, a general of the anti-canonical linear system, then such a curve will be irreducible, reduced curve with arithmetic genus equal to 1. We're not even saying that it's smooth. Probably it is smooth, but we don't really need this. We just need that it's irreducible and reduced. So it's not 3 lines, but we're fine with the nodal cubic curves. And in particular,
X as a Pezzo surface?
yes, X is a del Pezzo surface. That's the definition of a del Pezzo surface.
square is at least 3 or
No. This is just
Any kind.
the plan. In particular, we will see that this linear system has general members, which means that it has it has at least some global sections, and we will see that it has at least dimension 1, so that it makes sense to talk about general members, like it's not empty. Okay, but before we can prove this, we need 3 or 4 lemmas. Again, the first lemma 1, says that okay, we know already that H0 of the structure sheaf is equal to 1 because X is projective. But we also want that H1 is equal to H2, which is equal to 0. And here I also prefer to not go into too much detail, so this thing is 0, again by Rationality. So this thing here is the same as H0 of the canonical divisor, and the inverse to this line bundle is ample. And when we have a line bundle and when its inverse is ample, then that line bundle can't have any global sections. So this is equal to 0. But this one here is more complicated. So we get it for free if we use Creuder vanishing theorem, but that only works in characteristic 0. It's possible to either do a lot of work or use a very nice argument by Gruydenbeck where we consider the Albanese map for X instead. But I think we prefer to just use the Creuder vanishing theorem. So maybe I should state clearly what the Creuder vanishing theorem says. I forgot, what does it say?
If you have ample line bundle A,
There,
not line bundle,
vanishing.
divisor
If L
is ample,
Aha.
then higher homology of L plus canonical divisor is
0 when I is positive.
Yeah.
So here we just take L to be the anti-canonical divisor. And we get it free by this sort of advanced theorem, which works in characteristic 0. But actually this is true. This is 0 in any characteristic. But anyways, this theorem is still quite important. Okay, I want to erase this just so that we have space here for lemma 2. Lemma 2, which says that A H2 of any multiple of the anti-canonical linear system is 0. And it also says B, that H0, the global sections, the dimension, what?
For positive M. For positive
M is greater or equal to 0. Aha, спасибо. So this, part B, we get for free when we've proven part A of this lemma, because global sections of this line bundle must be at least the Euler characteristic, because H2 is 0 and H1 only subtracts. And we can compute this one using the Riemann-Roch surfaces. So this is equal to the Euler characteristic of the structure sheaf, which we see as 1, plus a half times, here we will have m times m plus 1. Okay, maybe we can just write 2 here, times kx squared. So if you want to check, we can check that we haven't made any mistakes here. So if x is the blow-up of P2 in 8 points, so let's say x is equal, like that I haven't made any mistakes here. So x is blow-up in 8 points of P2, and m is equal to 1, then we already know what the dimension of this linear system is, right? So if we have P2 and we blow up 8 points, then the anti-canonical linear system will be the pencil of cubic curves passing through the 8 points which we blow up. We blow up some points, and then it will be pencil of cubic curves through those 8 points. And that will be a one-dimensional family of curves. So the family is one-dimensional, which means that this vector space should be two-dimensional. And as I said, this is actually an no, I didn't say it. We will see later that this is actually an equality. But to prove that it's an equality, we need proposition 1, which we will show using this lemma. So this is actually an equality. So we claim that in this case, we should have two global sections here. And if we look, then m times m plus 1 divided by 2, m was equal to 1. So here we just have 1 plus 1. So everything is correct.
But if we apply the intervention theorem, we obtain it directly.
Yes. Yes.
H1.
But if we want to prove everything in positive characteristic also,
Yes.
and this lemma, we have some workarounds in positive characteristic. And this lemma, this is the workaround. But we also get this for free, yes. In characteristic 0. Okay, third lemma which we need. Lemma 3. So we also need that if C belongs to the anti-canonical linear system, then C is connected. How can we show that any member of the anti-canonical linear system is connected? We would like to do it in the same style as we've done before, so some homological method. So what is the condition for connectedness?
Compute H0 of X?
Yes. Yes. No, yes. We want to compute H0 if we can show or just OC. If we can show that this is equal to 1, then we can conclude that C is connected. And we can conclude this. And if we want to conclude this, we want to take our favorite short exact sequence. So we have 0 to O minus C to O to O C to 0. But O minus C is equal to O canonical divisor, right?
Yes. And by third derivative.
Yes, by Z-duality, this can have no H1. So H1 of Kx is equal to H1 of what by Z-duality? Yes, which we knew was 0. So we have no H1 here, and we have no H0 here also, because by Z-duality again, H0 here is equal to H2 of the structure sheaf. So we have no H1 and we have no H0, so H0 of this is the same as H0 of this, so this is equal to 1. We take the long exact sequence in cohomology of this short exact sequence. So we have mapped from H0 here to H0 here, so H0 here to H1 here. But H1 here is 0 and H0 here is 0, so the map from H0 here to H0 here is an isomorphism. Because the same argument, H0 will be equal to what? I said relativity. No, h2. X has two-dimensional.
In any case, it's C.
Okay, so C is connected, and I'm sorry for removing. Maybe I'm supposed to remove everything later, but I just want to keep the lemmas close to each other. So the fourth and final lemma, which we need before we can prove this technical proposition 1, says that if we have a non-irreducible or non-reduced curve in the linear system, in the anti-canonical linear system, then each curve is smooth and rational. And to show this, we will just need to show that the arithmetic genus is equal to 0.
So what is a suggestion of the lemma?
If we have any member of the anti-canonical linear system, yes.
But it can be non-smooth. So, for example, it's just one component and it's
Yes.
just you write that it's smooth. CI is smooth.
No. Each curve is smooth and rational.
So there should be some restrictions on AIs. I mean,
No, I mean that if just only one component and it's a it's a curve of
Which is
genus 1 but not smooth. It's possible.
you mean we have a line 3 times?
No, just this one. I mean that just this one, something like this. It's possible to be the component of here.
Not if we assume that this is not reduced or not irreducible.
I asked what your assumption?
Okay, sorry. Yes. So let's call this C. So yes,
Okay.
assumptions are important. We assume that C is either not reduced or not irreducible.
C is the sum or it's...
Yes, C is the sum, C is the curve. And it can have multiple components, and it can have, if it's irreducible, it will have multiple components. If it's not reduced, it will have some components with some multiplicities.
do we assume that AIs are positive?
Yes, because it's some member of some anti-canonical linear system. Probably I should point this out. So first thing we can say here is that this is at least 2. So in the anti-canonical linear system, we have at least a one-dimensional family of curves. And all those curves are effective. They're effective divisors. So we are taking such an effective divisor, and if it's irreducible, we're just splitting it into the components. And if it's reduced, we have some components with some multiplicities. And if we want to show that such a component is...
You understand what is mean multiplicities? So, for example, on P2, we have so the general element of the anti-canonical class is just a elliptic curve, yes. But of course it's possible, as I wrote, that it can be singular or even cascadal, also singular. But also it's possible that it was written here that it's like triangle. But also it's possible that it's a conic with a line. It's also a curve of degree 3. Also it's possible that it can be line, two times line and another line. So it means that it's a 2 with a C1 and C2. So it's a 2C1 plus C2. Also it's possible that it's a triple line. So this means that it's a 3C1 here. But it's a C1 is a line. Okay? So it's written here. So it's possible different configurations here.
So can you please help? Did you get that it's more equal than what was the
this number, maybe somebody else can see why this is at least 2. This number has to be what?
K square is bigger, not less than 1, yes?
Yes. Because it's simple, so some multiple of it will give an embedding into some projector space, and if we intersect some hyperplanes with a surface.
But of course, assumption that M is
yes,
bigger than 0. No.
Ah,
It's
okay.
Bigger.
It's positive.
It's not possible to be equal 0, of course.
Ah, okay, if it's bigger than 0.
Yes. We are asking about M equal 1.
Yes, when m is equal to 1, okay, it's greater or equal to 2 when m is equal to 1.
More than 1. Or at least 1.
It's also greater or equal to 2 when m is equal to 1. Okay, we want to show that these curves are smooth. And in this example, we see that it looks promising. And the way we can compute it is if we can show that the arithmetic genus of each of these curves is equal to 0, then, because the geometric genus is the geometric genus, this is bad notation I think, but anyways, it's at most equal to the arithmetic genus. And if this is 0, then this have to also be 0, which means that they're equal. So if they're equal, we can have no singular points because the singular point decreases the singular point decreases the arithmetic genus. The geometric decreases the geometric genus. So we just need to compute this geometric genus. How can we do that? We can use the formula, adjunction formula there. So the adjunction formula says that 2 times the arithmetic genus minus 2 is equal to the intersection number between Ci and Ci plus, right? Canonical divisor. And we need to somehow show that this is, if we can show that this is strictly negative, then we will be done. So we want to rewrite this. So this is equal to, equal should be here. This is equal to Ci intersected with Ci plus, is it plus there? Minus.
No, he is plus. He is plus.
Plus or minus?
Minus.
What? Where's minus? Where's plus? Plus here.
Yes.
Minus because C is minus
Because C
Okay. Yes. Okay. So we can write this as C plus, and we will have 1 over AI. So we would like this to cancel out with something. So kx. So should it be plus here, minus here, for this to cancel out with this? I mean, we write the canonical divisor in this as the sum. So we want the part of this anti-canonical linear system which has Ci in it to cancel out with this thing. So should it be plus 1 over AI or minus 1 over AI here? Minus? Okay. What? I'm just rewriting this. So here we have AI minus 1 divided by AI times kx. The point here is that this will always intersect this thing negatively. So we decrease this and we decrease this. So now if we write this thing out, plus here, and this thing here should cancel out with this thing here.
Yes.
Good. So what will we get? We will get some sum of all the components of the anticanonical linear system which are different from I, because the i's cancelled out with this one. So when j is not equal to I, so just from here, this part of a j divided by a I multiplied by ci times cj, right? Plus, okay, this is bad. This is very bad. I think I can remove the first lemma. I think we can remember the first lemma here. It's just about the cohomology of the structure sheaf of X. Okay, so this thing here is equal to a sum where j is not equal to I of a j divided by a I of ci intersected with cj plus minus okay, minus, yes. Plus, let's just put minus a I minus 1 divided by a I times ci intersected with minus canonical. And we see that this thing is negative, and this thing is negative. I mean, at least they are not positive. And if our curve C is not irreducible, then we will have at least two intersecting components because the curve was connected, which means that this thing here will be strictly negative if it's not irreducible, but if it is irreducible, then by assumption it will be not reduced, and if C is not reduced, then at least one of the coefficients will be at least 2, and then this thing will be strictly negative. What? So this thing is, this line bundle is ample.
Yes.
So it is effective. It must intersect all curves strictly positively.
Это общая вещь, что любое обильное линейное расслоение, будучи ограниченное на кривую, имеет степень положительную. Почему? Потому что его кратность задает вложение в проективное пространство. Соответственно, его кратность является дивизором. Дивизоры кривую любую пересекают положительно, строго положительно. Это необходимо, это на самом деле критерий обильности, что значит линейное обильное расслоение должно с любой кривой пересекаться положительно, строго положительно. Вот, поэтому вот это число всегда строго положительно, но тут, конечно, может, если это единство, вот это может занулиться, но вот это строго положительно.
Okay, so is it fine that this thing is strictly negative? So this thing can't be positive, and this thing can't be positive. And if the curve is not irreducible, then it has at least two components. And those components will add something negative here. And if it's not reduced, then at least one of the AIs will be at least 2. And this is strictly positive, so we get something strictly negative from this thing here. So this is negative, which means that the arithmetic genus has to be 0.
You're proving it for some I?
Yeah, for all i's. For all i's. So for all components of our curve divisor.
Can you please repeat your argument for the curve which is not reducible?
So if it's not reduced, then it has some component with multiplicity at least 2.
This is fine, this is alright.
So
And I'm about to tell you,
So if it is reduced, then it's not irreducible, and if it's not irreducible, then we will have at least two components which intersect each other because the curve is connected. So they will have strictly positive intersection with each other. And this number here, like these are just some positive integers. And this will be strictly negative. So that's everything.
Какой момент непонятный? Вот смотрите, значит, если у вас АИ больше единицы, это понятно, да? Тогда вот это число положительное, ну, не равно нулю, да? А это тоже положительное, ну, получается, что это строго отрицательное, да? Если оно равно единице, ну, вот этот член зануляется, тогда надо смотреть на этот член. И что вы должны увидеть? Что вот, как пересекаются цииты с другими цежитами.
Я понимаю, что цииты разваливаются.
А?
Цииты разваливаются на какие-то куски.
А мы вот доказали, что компоненты связаны.
Ну, в смысле, что они как бы...
Ну, смотрите, у нас...
Нет, все цииты неприводимы к кривым. Все цииты неприводимы.
Компоненты уже.
But we don't even need this.
Давайте рисуем, какая может быть ситуация. Вот такая вот может быть ситуация. Вот у тебя одна компонента C1. Дальше ты смотришь, как она пересекается со всем оставшимся. Она, конечно, с какими-то может по нулю пересекаться. Но со всей вот этой конфигурацией она не может пересекаться по нулю. Почему? Потому что если бы она со всеми пересекалась по нулю, они бы распались на две части, и она была бы не связанная компонент. Она связана, значит, с чем-то она пересекается, хотя бы вот со всей оставшейся вот этой частью, она пересекается положительно. Понятно?
Не может быть одна компонента с кратностью 2.
Может, вот даже с 3 может быть. Вот, но одна компонента, вот тогда вот это число, у нас вот это АИ двоечка, когда вот это здесь стоит что-то положительное, и это положительное, тогда это строго отрицательное, все равно. Мы сейчас доказываем, что вот это число строго меньше нуля, больше мы ничего не доказываем, а этого достаточно. Понятно? Чего не понятно? Спроси еще раз. Нет. Понятно? Почему не может 3? Может быть 2, может быть и 3, может быть.
Я понял, что мы еще не доказываем.
Не, мы просто доказываем, что вот это число строго меньше нуля, то есть что род у нас вот, что род у нас 0. То есть вот это число может быть меньше нуля только в одном случае, когда GA равен нулю. GA бывает либо 0, либо 1, либо 2, во всех остальных случаях это число больше равно.
So this is just some teaser for what will happen later. Okay, so now using our for lemmas, we are ready to prove proposition 1. So yeah, I'm sorry about leaving this. Okay, so proof. So we proceed by contradiction. Assume for contradiction that we have a curve C, which we can write as a sum of AI times CI, with CI being smooth and rational inside our anti-canonical linear system, and assume that C is general. And we want to obtain a contradiction. And the contradiction we will obtain is that we will see that the linear system, we will compute the linear system of C and see that it will be too small according to our lemma 2, here. So the way we compute it is we have H in, so I will just write the inequality and then we can discuss why it might or might not be true. C is equal to H0 C I. So here the CIs, by CIs, we take not all of them. So if we could have, say, M here, M components here, and here we will have, say, the first M prime components, which are moving inside the linear system. So we are assuming that we have a curve here inside our anticanonical linear system, and we can write it in this form. Some of these curves, Ci, will be moving, which means that as we vary, those curves will vary, which means that H0 of Ci will be at least 2. Then they will be moving. And the claim here, which I think we should be quite careful about, so I'm still only like 90% sure that it's actually true and arbitrary characteristic and all of this. But the point is that because x has, so h1 of x of the structure sheaf being trivial somehow implies that the Picard group of x is a lattice. Lattice.
То есть это значит, что у меня нет непрерывной части, как, например, на эллиптической кривой.
X0 is empty. So the point here is that if we have an elliptic curve and we take a divisive degree 2, it can be written as the sum of 2 points. And as we are varying inside this linear system, those 2 points will vary. And this point, they will go into different linear systems. So each of the points will vary inside X0 of the elliptic curve. But, okay, it's 1 point, okay, here. But because our Picard group is discrete, when we are varying inside our anticanonical linear system, somehow it's not possible for these curves to jump between different linear systems. So I think over complex numbers geometrically, it's easier to be convinced about this. So we have some curve, a general position. It has some components. And the curve is very, very general. And when we are varying the linear system, some of the components will remain fixed, and some of the components will vary. And they will each vary inside the same linear system. So if C is general, the claim is that if we take a C prime inside this anticanonical linear system, then the claim is that we can also write C prime to be equal to the sum of AI. The weights should be the same. The curves may be different, but each curve is equivalent to before. This is the claim. And that's because the Picard group is discrete. And again, this is pretty clear this is somewhat clear over complex numbers. In positive characteristic, I'm still only 90% sure, to be honest. But if we accept this claim, which I feel is the most questionable part of this.
What do we claim?
They claim
This inequality is true? Or?
We claim that if C is general and we can decompose it as a sum of other curves with some multiplicities, then for any other curve in the anticanonical linear system, it will also decompose as a sum of curves which are equivalent to the CIs. I'm not claiming that these curves are smooth and irreducible even. They might decompose further, but
Давайте несколько слов по-русски. Значит, вот предположим, у нас, значит, что мы хотим? Мы смотрим, что это вот какое-то, у нас опять вот такая вот какая-то конфигурация, там C1, C2, C3, C4, тут может быть они с какими-то кратностями взяты, но главное, что это общее, то есть вот мы его рассматриваем как общее general, что оно вот general, то есть написано, ну в общем, да, вот что это значит, что оно general? Это значит, давайте рассмотрим его деформации вот в этой линейной системе, собственно говоря. Другие сечения, значит, то, что оно общее, это означает, что его все деформации стоят в следующем. Это деформации каждой из этих отдельных компонентов. Потому что если, например, две компоненты вместе перешли во что-то другое, вот во что-то более, то значит это было не общее. Значит, что у нас общее? Понимаете, да? Раз мы предположили, что это общий элемент, это значит, что все его деформации, это деформации, собственно говоря, ничего другого нет, кроме как деформации по компонентам. Вот. А по компонентной деформации это вот как раз вот эти вот пространства, вот, которые отвечают за каждую деформацию из них по компонентам. То есть по факту любой другой элемент, он у нас складывается из, имеет вид АИТ, СИТ штрих, где СИТ штрих это деформации вот этих штук. А теперь Алекс говорит то, что надо еще только заметить, что вот все вот эти вот деформации ЦИТы, что вот эти ЦИТы штрих, они на самом деле линейно эквивалентны ЦИТам. То есть вот на эллиптической кривой это неверно, что если вы вот здесь точечку взяли и чуть-чуть сдвинули, то вот это не, она, конечно, деформация этой точечки, но как линейное расслоение, это другое расслоение, оно не эквивалентно линейно, понятно, да? А в нашем случае, так как у нас пикар дискретный, то есть это решетка, у нас нет непрерывной части, поэтому любая как бы деформация ЦИТова, ну вот просто деформация в смысле в семействе каком-то взяли вот эту вот кривую и вот чуть-чуть ее сдвинули, то она на самом деле и линейная, она не только алгебраическая, она линейно эквивалентна этой системе, потому что у нас у пикара нет непрерывной части. Вот то, что он дискретный. Ну и отсюда следует, что у вас любые элементы вот из этого пространства, ну здесь размерность написана, но вот из этого пространства, они на самом деле складываются из компонент. Ну отсюда следует, что вот это пространство, эти там подпространства, вот, но эти подпространства все порождают. Ну значит их сумма больше, чем сумма всего пространства. То есть получается вот это вот не меньше.
I'm still a bit confused. If we are working in some small characteristic, then X is also more or less discrete, and why it's not possible to have some family of curves which over one point looks like a line and a conic, and then it becomes three lines, and then it becomes the two new lines go to a conic, and the third line stays a line. Why we know that the components vary? Like, why are we sure that they're varying? It's not.
I think that everything is working because, as we discussed, it can be. We know that it's a rational curve. We can restrict it and show that it's in the same linear system.
But what are we restricting? We are restricting subfamily. Yeah, but that assumes that these moving parts can be chosen. We have a family which is irreducible, and we are assuming that we can choose one of the components. To me, it's not totally obvious that we can really choose one of the components. I mean, okay, well, maybe the components can be permuted with each other. There can be some action by some Galois group if we're working over enclosed fields, and maybe we need to take some metal cover.
I don't think that there is some kind of problem here.
Okay. So if we're just assuming this inequality here, then we can finish. So we're assuming that this is a decomposition of vector spaces. Then we need to count H0 of Ci.
So what is
In prime is because we are forgetting about the components which are not moving. So some of the components might be fixed in the linear system. I mean, you could imagine that we have, like, our surface could be blown up in some point, and we could have the linear system could be a linear system of the union of a line, a strict transform of a line through the point, and then an exceptional divisor. Then you can imagine that we have a linear system. Then the line here is varying, and the exceptional divisor is fixed. So the line here will be the moving part. And we can forget about... They're not adding anything to the dimension of the linear system. So we need to compute these things. And we can compute this because we know that they're smooth now, using, again, our favorite short exact sequence. OX x of ci O of ci restricted to ci. This one. And we want
too many CIs.
too many.
Remove one of them. No, I think that's
I can remove this one.
yes. It's enough. Yes.
Then we know that h1 of this one is 0, which means that h0 of ci, I'm adding more, is equal to h0 of ox plus h0 of then ci of ci restricted to ci. And this thing here is so this thing here is 1. And this thing here is equal to the degree of the restriction of this divisor to the curve ci plus 1, because ci is isomorphic to p1. So we have this. Now we can continue the computation up here. So this is equal to
What is d squared?
sorry, ci squared. Because the degree of this here is a divisor on ci, which is isomorphic to p1, and the degree of that divisor is equal to the self-intersection number of ci. We knew that ci was moving, so we can pick another member of the linear system of curves isomorphic to ci, and they will intersect transversally in some number of points, and that number of points is equal to ci squared. So this sum here is equal to the sum of 2 plus ci squared.
Why you add one another time?
Because this is h0 of p1 of OD is equal to d plus 1. Okay. Okay, and so we have this one here, and this is at least equal to, now I have to, minus kx intersected with sum of the ci's. Is this thing clear? So we can write kx as the sum here. And if the alpha i's are positive, then it will only make this thing bigger. So we can assume that all the alphas are equal to 1. Then when we are taking the product here, we will get some of these ci squared. And we will also get ci intersected with cj. And here we are using that it's the whole curve C is connected. So these 2's will come from intersection numbers between curve Ci and Cj.
And if C is just one curve, which is like, if it's decomposed, just...
You mean it's reduced, but not irreducible. If it's reduced and not irreducible, then we will have 2 plus Ci here. You are saying then this will not be greater than this. If it's reduced, then A1 will be at least 2. Right?
Why is sandwich just irreducible and reduced?
No. We are assuming for contradiction that the curve is not irreducible or that it's not reduced.
Okay, then it's reduced.
And I agree, this inequality here might not be totally obvious. So we need to do like 2 different cases. If it has only one component, then A1 1 will be at least 2, and then we can see that this equality will indeed hold. And then when it will have more components, then these 2's will come from intersection numbers between different components. And we can check this explicitly, but I would prefer to not do it as some combinatorical thing. We can draw a graph of the curves which intersect each other, and we can see that the number of intersection points will be at least equal to the number of components minus 1. No. Yes.
I don't understand.
Okay, you want to prove this?
I don't know, but I don't understand why it's true. I don't see it at this moment.
Yes, I should have thought more about this one. Okay, so this thing here is equal to a sum of a I times ci intersected with sum of ci, right? This thing here is equal to this product. And in this product we have some, we for sure have all the ci's here. It's equal to ci squared, right? What? Yes. Plus ai plus aj times sum of ci intersected with c2aj times sum of ci intersected with cj. So if we're just summing over pairs of I and j.
So you have pair and it's with different coefficient, aj and
Yeah, but here we have just ci.
Without 2. So we have without 2.
Without.
It's without 2. Okay, so we have just a j there. Okay, so
So at first we don't know that ci square is positive.
we know because they are moving parts.
Okay,
So each ci squared is at least 1.
let us fix it.
Okay, ci squared is greater or equal to 1.
Why 1? Why it cannot be 0, for example?
Okay. Okay, maybe it could it be 0? Okay, it could be 0.
No, I just ask.
Yes. Okay, I'm sorry, I just read this.
I don't know what is written there. So I just.
Okay, but anyway, we don't have enough tools, right? We have one less. We have only n minus
1. This is an equality. This is the adjunction formula
It should be something like this.
because it's rational.
Okay, it's better show.
So because it's rational, it means that ci squared plus 2 is equal to minus kx intersected with ci
Yes.
by the adjunction formula. So this is not an inequality, this is in fact an equality. So the adjunction formula was this one here. And in our case, this will be 0. And here we have ci squared, and then we have c times ks, and that's where we get the 2's from. And that's why lemma 4 is so important, that all the curves are rational. So here we have an equality, and then we get an inequality, minus kx squared. Yeah, sorry for this. Then by lemma 4, no, by lemma 3, no, by lemma 2 here, when we put m to be equal to 1, we saw that this h0 must be at least 1 plus kx squared. But this is strictly less than minus kx squared plus 1. So that's a contradiction.
Can you say again, okay, if we understood this equality, then we say that why it's not greater than this?
Because kx it's sum of ai times ci, and we're using that ci squared and is a non-negative, and ci intersected with cj is non-negative.
And why it's
So that's true because we assume that these are the moving parts. That's where the m prime here came from.
yeah.
So we can pick two elements in the linear system which are not identical, so they will intersect each other transversally. And then the intersection number will just be the number of intersection points, which is non-zero. It could be 0. So that's how we get this inequality.
And then we are saying that, it's this. And what is the contradiction?
The contradiction is by lemma 2 here.
So,
Okay.
with inequality, you accept this
Yes,
inequality?
yes.
Okay.
No, I just need to see it, it's fine.
This is just evident.
Yes,
And
yes,
this is
yes.
just by this form.
Okay, so this finishes proposition 1, which is mostly technical, and now we can continue to the nice stuff. So now we've proven the most technical stuffs. And the first result is theorem 1, which has 3 parts. The first part says that if we have a line bundle L with degree of L, I'm sorry, I need one more lemma, which will be an improvement. Yeah, so this lemma 4 is not important anymore. So let's say lemma 5, which is strictly better than lemma 2. So is it fine with everybody that now that we know that C is irreducible, it's clear that it has arithmetic genus 1 because it belongs to the anti-canonical linear system. So by the adjunction formula, it has trivial canonical class. So the canonical class of C is equal to the canonical class of X minus the curve C restricted to the curve C, but plus. But this is C is equal to minus kx, so this is 0, which means that the arithmetic genus of C is equal to 0.
1.
Is equal to 1. Okay, so that finishes proposition 1. Then lemma 5 says that this equality here is in fact an equality. So h1 of minus k of x is equal to 0, which will automatically imply that h0 kx is equal to 1 plus m times m plus 1 divided by 2 times kx squared. And now we can compute h1 here, because we know that C is a genus 1 curve, so we can prove it by induction on m. So when m is equal to 0, then it's just lemma 1, because this is the structure sheaf, so we are done. And if we want to do the induction, we consider again our favorite short exact sequence, Ox minus mkx to Ox minus m plus 1 kx. And then here we will have OC, where C is a general member of the anti-canonical linear system, minus m plus 1 kx. And C is a irreducible reduced curve of genus 1. So we can use the effects which we discussed here. So H1 of this line bundle will be trivial when m is at least 1. And then by the induction, by the induction, we know that h1 of this thing is 0. So when h1 of this thing is 0 and h1 of this thing is 0, we can conclude that h1 of this thing is 0 by taking the long exact sequence in cohomology. So this is...
Непонятно? Ну, он просто хочет показать, что по индукции, что h1 вот от этого равен нулю. Если мы знаем, что h1 от этого равен нулю и h1 от этого равен нулю, но он между ними, то он равен нулю. Значит, по индукции, это, если это по индукции идет, значит, мы предполагаем, что это мы знаем. А это следует вот из этого факта, что h1 равен нулю, потому что это положительное число здесь на кривой, да? Положительное линейное расслоение в степени больше нуля. Значит, у него h1 равно нулю на кривой. Это вот из этого факта следует. Ну, значит, это h1 равно нулю. А база индукции, вот m равна нулю.
So even if m is equal to 0, this, when we take the restriction, it will still have degree at least 2 because of this inequality. So this was at least 2. So this restriction have at least degree 2 on the curve C. So this is an improvement of lemma 2. Okay, this was the final lemma. Now we can do the fun part. Part A. L, if we have a line bundle L and the degree of the line bundle on X is at least 2, then the linear system, if we have minus m times kx squared is at least 2, then the linear system minus m kx is 3. Part B is so this is just a version for del Pezzo surfaces of this one. Then we have a version of del Pezzo surfaces of of this one. So
What do we assume that there is
what?
negative or positive?
Kx is the canonical divisor.
Yeah, I see.
Okay, m will always be non-negative. Okay, we can assume that it's bigger than 0.
Ну да, то есть здесь, собственно говоря, есть только одно исключение, по сути. Когда m равно единице, когда m равно единице и kx в квадрате равно единице, только единственное исключение, понятно, да? Если хотя бы одно из них больше единицы, то это больше равно двойке. То есть фактически всегда, вот, значит, эта система, она всегда свободна, но за исключением одного случая m равно единице, а kx в квадрате равно единице. Вот все, больше ничего нет.
Okay, the next part of the theorem says that r less than or equal to alpha of x minus kx generates the whole ring. And finally, C, if the degree of x is at least
I didn't understand.
the first where alpha is equal to 3, 1, 2, 3, if kx squared is at least 3, 2, and 1. So depending on the degree of x. So if the degree of x is at least 3, then we will see that this is in fact very ample, so the whole graded ring here is generated by R1. And if it has degree 2, then it will be generated by the first 2 components, and if it has degree 1, then it will be generated by the first 3 components. Then the C, that's the important part. So these are a little bit more technical, and the C important part says that if the degree of x is at least 3, then
Здесь могли бы написать, you can write that alpha k square is the same, like that. Forget it.
how is possible? Then minus kx is ample. So C here is the important one. Very ample. Okay, let's start by proving the first one, A. So I need to remove something. I think I can remove 3 here. 5 is the only which is left, which is important. So we consider again our favorite short exact sequence, which is O to O x minus m minus 1, kx to O x minus m, kx to O c, where c is general member of the anticanonical linear system, minus m kx restricted to c.
То есть понятно, что мы доказываем в пункте А, да? Что система свободна. Понятно, что это значит, да? Что с любой точки можно измениться.
In the first row, left shift, probably there should be minus. No. First row. Yes. M plus 1.
No. Let's try it. This time I'm right with the signs.
Это минус m плюс 1.
Because c corresponds to minus kx. So we need to make it smaller. We need to make the coefficient before kx smaller.
Минус kx.
C. Okay, so we want to show part A. We want to show that it's free. And the idea is that assume for contradiction that this linear system has some base points. Then first, those base points, let's call it B. Let B be a base point for this linear system. First, we conclude that B is contained in this curve C. So if we have a base point, this is a linear system. If this linear system has a base point, then I claim that base point.
So you want to prove that this linear system minus mkx is free?
Yes.
Okay. And now you assume opposite.
Yes.
Okay.
Assume for contradiction that it has a base point.
Okay.
Then I claim that base point has to be contained in the curve C. And that is because the mth multiple of the curve C is itself, so m times C belongs to this linear system. So if this linear system has a base point, the base point has to be contained in this curve.
Понятно это? А? Ну, что такое точка? Значит, мы хотим доказать, что с любой точки можно съехать. Да? Что для любой точки существует что-то, проходящее вне этой точки. Вот что мы хотим, да? Ну, какое-то сечение, которое эту точку не задевает. Вот. Ну, понятно, что у нас вот есть одно из возможных сечений, это то, просто кривая c, взятая m раз. Поэтому для любой точки вне кривой c, ну, мы уже показали, что существует сечение, которое ее не задевает. Поэтому если существует байсная точка, то она на самом деле, что такое байсная точка? Она лежит на всех компонентах, на всех сечениях, которые мы могли бы провести. Ну, в частности, именно на C, которая MC, которая тоже является таким сечением. Понятно, да? Значит, если байсная точка есть, то она заведомо лежит на C.
Okay. Yes, and how can we complete the rest of the argument? So as we are assuming for contradiction, we have some basis point. We've concluded that that base point is contained in the curve C. Yes. So basically, because we know that the restriction of this linear system to the curve C is base point free by these facts which we discussed here. So the restriction to C can't have any base points. So if it had a base point and this is a surjection, then it can't have it. We get a contradiction. Okay, so that's part A here. So now we need to do part B. And I need to erase something. Is it fine if I just erase this, which I've just... And for part B we will do induction. So we will show that R alpha generates less than or equal to alpha generates... I just removed what I needed, sorry. Generates Rm for all m. And we will show this using induction and m. And the base case is clear. I mean, if m is equal to 1, then we for sure know that less than or equal to alpha generates R1. So we just need to do the induction. And then I need to draw what I just draw. So we have this short exact sequence of cohomologies, which I just erased. Minus m minus 1 kx h0 x minus m kx.
I'm sorry, I just stop you one moment. Let us return back. Значит, доказательства все поняли, да? Но все ли поняли, почему здесь вот все-таки m равно единице и kx квадрат как раз не подходит? Ну, мы вроде для всего доказали, а на самом деле не для всего. Да, вот m равно единичке и kx квадрате. Оно не подходит. Почему не подходит? Понятно или нет? Что там нарушается? Вот он рассуждал, и всех как бы немножко обманул. Ну не в том смысле, что обманул, он просто что там не подходит? Там, значит, да, то есть вот у вас кривая c, да, и вот ограничим вот это, вот, значит, у нас что здесь m равно единице, да, kx мы ограничиваем на нашу кривую c, да, что мы здесь получаем? Что это будет за линейное расслоение на кривой на этой c? В какой степени? 1. Степень 1, да, это будет линейное расслоение. Какой? У нас kx в квадрате равно единице, m равно единице. Да? Вот это вот kx. c, оно само принадлежит kx, да? Значит, что вот это расслоение, будучи ограниченным на кривую c, имеет степень 1. Значит, это будет линейное расслоение степени 1 на эллиптической кривой. Оно связано с одной точкой. И эта точка неподвижна, она не двигается. Там только одно сечение, как раз в этой точке зануляющееся. То есть вот эта точка на этой кривой, она и будет базисной точкой вот этой всей системы. То есть почему это не проходит для m равно единице и kx в квадрате? Вот ровно потому, что вот эта точка, то есть у нас там будут как раз ситуация, какая ситуация будет, что у нас, вот когда kx в квадрате равно единице, у нас, значит, на этой трапеции степени 1, у нас пучок, то есть можно вот кривые можно варьировать, но все эти кривые будут поворачиваться вокруг вот этой точки P, через которую они все будут проходить. И это будет вот эта точка базисным множеством. То есть вот это единственное, собственно говоря, исключение, ровно потому что здесь вот на кривой C это степень 1, оно не является тоже не является системой.
Yeah, so this is the picture. We have the blow-up of P2 in 8 points, and the anti-canonical linear system is the pencil of cubic curves through those 8 points. And we know that this pencil contains one other fixed point. So it's not free. Okay. Now we want to show part B. And for part B, we use induction. So we know that the first alpha components of R generates this vector space, which means that it generates the image in here. We also know that when we restrict this, these first components are less than or equal to alpha to the curve, then we restrict it to the ring, to such a ring on the curve. And we assumed, we took this for free, that this ring on the curve is generated by the first alpha components, which means that we know that the first alpha components of our ring on X, when we restrict it to the curve here, it must generate this vector space, which means that the first alpha components of our ring must also generate this vector space. Okay, so I think it's worth probably to look at it this a little bit more, but we want to go to Theorem 2.
Все сводится к кривым, то есть вот как раз с помощью вот этой последовательности все можно свести к тому, что эту систему ограничить на кривую. Там увидишь, что там порождается, ну а наверху вот это промежуточное пространство, оно является суммой вот этих, как бы, ну, как бы оно зажато между этими двумя пространствами. Все. Отсюда все как бы получается банальным образом.
Okay. And now we can conclude part C, right? So part C is just the case, this case, when x has degree at least 3. Then we know that R1 generates the whole ring. And then we know that this line bundle, then it's a canonical linear system, is not only ample, but it's very ample. Okay, it's not a linear system, which is a line bundle, which is very ample. But, is that fine? Okay, now we can proceed to the main theorem here.
Can you repeat the proof of C?
Yeah, yes. So if x has degree at least 3, then our alpha is equal to 1, which means that R1 generates the whole ring R. And then we made this argument in the beginning where we constructed a surjection from this graded ring. Okay. So this theorem here is important. It means that for all the Pezzo surfaces of degree at least 3, we can embed them in projector space, and using lemma 5 here, we can compute the dimension of that projector space. And now we will do this and make some concrete calculations for the Pezzo surfaces of degree 1, 2, 3, and 4. And again, this works in any characteristic and over any field, so this is quite nice. So let's start with the easiest case, which is when x is degree 3. When x is degree 3, then the anti-canonical linear system is already ample, and it induces an embedding of x into very ample. Okay, maybe somebody can.
So what is xc and this?
Xc, x is embedded.
It's not xc, it's
embedded in what? So when x is degree 3, then we can use the anti-canonical linear system of x to embed x into a projectorization of h0 x of minus kx.
Теперь выясняем, в какие проективные пространства мы попадаем с помощью вот этой очень обильной системы. Да? Ну, вот мы выяснили, что при kx квадрат больше равно 3, эта система является очень обильной. То есть она куда-то складывает, какое проективное пространство. Ну вот какое проективное пространство? Проективизация вот этого пространства. Собственно говоря, просто надо посчитать, вон, где тут бывает формула, размерность этого пространства.
Yes.
It is more canonical to write to.
Aha.
What does it mean, the third column?
This is just the description, so it will be some hypersur, it will be some divisor, it will be some complete intersection of divisors.
Ну вопрос, значит, при k квадрат 3, в какое проективное пространство мы попадаем? Помните, там формула была написана?
На левой доске сверху.
Lemma 5.
Да, вот это, да. Куда, что там стоит? Вот где знак вопроса. Какой фэс? А? Чего? Ну давай считать. R равно единице. K квадрат равно тройке. Чем? Где единица?
Сейчас, квадрат уже.
K квадрат равен тройке. 4. Но проективизацию берем. Проективизацию что? Значит, проективизация четырехмерного пространства это что? P3. Значит, там попадаем в P3. Ну а дальше тоже там, ну формула простая. Прибавим единичку, а потом выше единичку.
So what will be here? Is this the budget?
P4. Ну да.
Okay.
Ну и так далее. В общем, все ясно.
Yes, but so this is an embedding of a smooth surface inside P3. So the image must be a divisor. Then the question is, what will be the degree of this divisor? Will it be a quadric? Will it be a cubic surface? What will it be? How can we find out? Yes. So if we take let's call the embedding phi. So if we take phi of x and intersect it with the hyperplane in P3, we should get how many points? And one hyperplane, what did you say?
Короче,
Yeah, two hyperplanes.
Вопрос простой. Мы попали в P3. Что получилось в P3? У нас поверхность P3, она что имеет? Степень. Какой степени поверхности? А?
Ну, надо умножить на две плоскости.
А что посчитать надо? Ну да. А что получится? Какой степень, чему равна степень? 3. Почему 3? Потому что степень чему равна?
Минус 300.
Kx квадрат, конечно. Степень равна просто kx квадрат. То есть мы попадаем, это какая-то получается поверхность в каком-то пространстве. Какой она степени? Эту поверхность надо пересечь с одной гиперплоскостью, с другой гиперплоскостью и получить количество точек. Но эти гиперплоскости это и есть антиконкласс. Значит, их пересечение это просто степень этого антиконкласса, с чего мы начали, kx в квадрате. Понятно?
So I want to show it in another way at the same time, which makes the next one a little bit simpler. So here. Yeah. So we have the ideal sheaf of x inside P3. And if we want to find out if it's contained in a cubic surface, we must find the global sections of the ideal sheaf tensor 3H. So we should find the global sections of this line bundle. And what's the global sections of this line bundle, and what's the global sections of this line bundle? So this line bundle has how many global sections?
What are you doing?
Trying to argue that the image is contained in a cubic surface in another way, by computing global sections of this ideal sheaf tensor O3.
Okay.
And we take this short exact sequence tensored with 3H, and then if we can find one global section here, then the image must be contained in one cubic surface. And because we will need to show that the same is not the case, technically we should do the same for a 2H to show that it's not contained in a quadric, and so on, so that we make sure that this cubic surface is irreducible, and then we conclude that the image is contained in a cubic surface.
So you want to show that Lx is a O minus 3, yes?
Yes.
You want to show that Lx is O minus 3H.
Yes.
Minus 3, yes?
So we need to show that this has one global section, and we count here, so this is the same as we have 4 variables, so it's equal to 6 choose 3, which is the same as 20. And we can compute this thing using lemma 5, which is equal to 1 plus 3 times 4 divided by 2 times 3, which is equal to 19. And we know that this has to be a surjection, because the line bundle is very ample. So the kernel here, we get one global section. That's just another way to prove it. It's just another argument. So, let's try do the fourth case when x has degree 4. Can anybody guess what the image should be?
Значит, мы получаем, в случае P3 все понятно, мы получаем какую-то поверхность в трехмерном пространстве, она имеет только степень. Здесь мы получаем тоже степени 4, что-то в P4, но она уже по размерности 2, и в принципе поверхности в P4 степени 4 могут быть разные. Вот. Вопрос, что это за поверхность, как ее можно по-другому описать, эту поверхность степени 4 в P4. Ну вот он предлагает вам угадать. Какого она типа? Да. А? Да. Ну вот да. В каком пересечении чего с чем?
Да.
Да, правильно.
And how can
правильный ответ,
да. And how could we actually prove this? So I would prefer to. So first, it's clear that the image can't be contained in a hyperplane, because if it was contained in a hyperplane, then the global, because the global sections of this variable line bundle has dimension 4, so it's density canonical embedding, it can't be contained in a hyperplane. So if we can show that it's contained in a pencil of quadrics, then we will be done. Then it must be a complete intersection of two quadrics in that pencil. And then I propose using a similar method to here. So we consider the image of X inside P4, and we consider the ideal sheaf of X. And we tensor it now, this time with 2H. And we want to show that it's contained in a pencil of quadrics, so we consider 2H here and 2H here. So what will be, and we know that when we take global sections, this must be a surjection. So what will be the dimension of the global sections here? So what is H0 of X of 2H is equal to what? And what is the dimension of the global? How much? Who agrees? Here. Okay, 13. And here? What? Da. So we have 3 variables, we have 4 variables, so it's like this, which is the same as 5 choose 2, which is the same as 15. Which means that we get 2 global sections here, which means that X is contained inside a pencil of quadrics. So X is contained in the intersection of 2 quadrics, and this intersection can't be, it must be irreducible, because otherwise it would be the union of 2 planes, and we know that the image is not contained inside a plane. To H, complete intersection. Now, what can we do with 1 and 2? So now the anti-canonical linear system is not very ample anymore. And now the best, so of course we could take some power of the anti-canonical linear system, and we could embed our del Pezzo surface into, I think in this case, P6, something like this. But that will not give us a very simple description. A simpler description will be as in this case, as divisors on some weighted projective spaces. So let's do this one first. So assume that X has self-intersection number 2. So we are considering a del Pezzo surface of degree 2. What will the anti-canonical linear system give us? X. So we know that the...
Let me say just one thing that I said before. So we can consider also 5, 6, 7 here, and we have embedding to P5, P6. Ну, мы имеем вложение в P5, P6, но уже вот здесь P5 мы уже не можем там, понятно, это описать, вот как здесь, как полное пересечение. То есть понятно, что дальше это все сюда вкладывается, но эти поверхности уже так вот легко не описываются там в виде полных пересечений. Понятно?
А какое-то описание все равно же есть?
Ну, оно как бы, оно не то чтобы сильно нужное, как бы так скажем. Потом будет видно все по-другому, что все можно сделать как бы в каком смысле. То есть оно не то чтобы очень нужно.
How did you get that the curve in P4 is contained in the tensor?
By showing that the ideal sheaf tensor 2H has exactly 2 global sections. So the H0 of ideal sheaf tensored some line bundle L is exactly the linear system of divisors in this linear system containing our variety X.
Ну давайте, вот смотрите, значит, вот это вот просто, вот сечение вот этого пучка, это просто все квадрики в P4. Дальше вы их начинаете ограничивать на вашу поверхность. Какие-то из них переходят вот сюда, значит, не в ноль, то есть вот они как-то пересекаются с вашей поверхностью, а какие-то сюда переходят в ноль. Что значит, что вот эта квадрика, сюда, это сечение, сюда в ноль это выражается? Ну, значит, она вот полностью содержит вашу поверхность. То есть вот она здесь оказывается. То есть вот это 15 минус 13, у нас получается, что у нас двумерное какое-то вот здесь подпространство в этом 15-мерном, да, пространстве состоит из тех квадрик, которые сюда прямоугольницы в ноль, то есть значит они полностью содержат нашу поверхность. То есть они через нее проходят. Значит, у нас есть двумерное семейство, значит, у нас, ну, по крайней мере, можно базис выбрать, там одна квадрика и вторая квадрика. Ну и вот их пересечь. Пересечение двух квадрик это уже что-то получается степени 4 и размерности 2. И у нас степени 4 и размерности 2. Ну, в общем, более-менее вот оно и все и получилось.
So we have 10 minutes left, so there are like three options. Either I speed run the last two cases, that's probably not a good idea. I try to do only one of the last two cases, or I spend 20 minutes instead of 20 minutes.
As you prefer, yeah, you can, I think.
20 is fine.
I think.
So at this moment you want to talk about weighted projectors?
Yes, about the embedding.
Yeah, okay, but before to talk again, before to talk about weighted projectors space, let us say that what we have here. So Alex explained how we embed to the weighted projective space, but I just say what we have here, if you consider map by using the canonical class. Look, P3, P4, P5, what is here? P2. And moreover, более того, это система свободная. То есть у нас есть отображение из нашей X в P2. На самом деле, так как система свободная, то это очень хорошее отображение, и можно даже посчитать степень этого отображения. Так как наша kx в квадрате равно двойке, а здесь гиперплоскости по единичке пересекаются, то это отображение на самом деле степени 2. Это просто двулистное накрытие P2. То есть наша поверхность можно написать как двулистное накрытие P2, ну, с ветвлением в некоторой кривой. Это будет потом, видимо, все сказано. Но сейчас нам предлагается рассмотреть не это отображение, а вложение x в взвешенное проективное...
Никакой ответ, никакой, no spoilers.
Взвешенное проективное пространство, но оно будет вот это с помощью канонического класса отображения, а здесь у нас будет удвоенный канонический класс, правильно?
Ну, посмотрим, что узнаем. Так. Так. Yes, so the anti-canonical linear system gives a map from x to P2, because this linear system is space point free. And what this means, how is it? Okay, so because we know that minus 2k, where do we have the lemma? Theorem here. We know that r less than or equal to 2 generates the whole graded ring, right? Which means that r less than or equal to 2 generates the whole graded ring, kx. And now we apply the thing which we discussed in the very beginning, which was that if we take inside R1, if we have a 1, 1, 1 is 1 generators, and then inside R2 we need additional B21, no, A21, A2S2 generators. So, which means that R2 is generated by the image of this squared inside R2 plus additional S2 elements. Then we argued that then we can embed X inside the weighted projective space. Where we have S11s and S22s. So we just need to find out how many elements from there are in R1 and how many additional elements we need from R2. So how many elements are there in R1?
Чему равно S1?
Да. because it's just the global sections of the anti-canonical linear system, which generates this map. Then, because we have this morphism, it means that inside here, inside Pezzo, we have the map from symmetric square of H0, P2, O1 to H0, P2 of O2, right?
Теперь надо посмотреть, сколько нам не хватает там. Почему равно S2 сейчас считаем?
And yeah, and this vector space is 6-dimensional, and this is a surjection. And this means that we can take all these sections and lift them to X. So then the question is, why doesn't any of these sections vanish on X? So I'm claiming here that the image of R1 squared inside R2 is 6-dimensional. I'm claiming that none of these sections here, when we restrict them to X, vanishes. Why is that the case? So assume for contradiction that one of these sections vanishes. What would that mean geometrically? Yes, a conic. Yes, exactly. It would mean that the image would lie in a conic. So why can't the image of this map not be a conic? What? Aha. Some argument about degree.
Yeah.
Assume for contradiction the image was a conic, then what would we get?
Ну, в общем, он не может быть на такую, то есть он не может попадать в что-то меньшей размерности, чем P2, иначе бы степень была равна нулю.
Because we would intersect it with 2h, and then we get no points.
Yeah.
So the degree would be 0, so that's absurd. So all the sections here will become non-trivial on X, which means that the dimension of the image of the map from symmetric square of R1 to R2 is at least 6. It can't be greater than, it also can't be greater than 6. So it has to be equal to 6. So how many additional elements from R2 will we need to take?
Посчитать надо размерность. Чему равна размерность? Минус 2kx. Вот там kx в квадрате равно двойке, m равно двойке. Что получается? 7. 6. А здесь 6, значит не хватает одного. Почему? Здесь 6.
R2 is a 7-dimensional vector space.
6 мы уже получили.
The image of this map is 6-dimensional, so we need one more.
Да, не хватает одного.
Which means that we can embed x into p what?
3 раза по одному.
Aha. E. Da. Okay, next thing which we don't have time for, I think it's more interesting to find out what is the weighted projective space here, is that this will be equal, okay, maybe somebody can guess what will, so we know that the device, the class group of weighted projective space is singular, but its class group is generated by H. Do people know what is the self-intersection of H inside this weighted projective space? What? Probably you've listened too much. Somebody else? What is H to the power of 3 inside this weighted projective space? So the point is that H is defined by x0 equal to 0, or this equal to 0, this equal to 0, this equal to 0. If we just intersect 3 such devices, we will get a singular point. So in order to get a non-singular point, we will need to intersect this one equal to 0 and some of these. Then we will get a non-singular point. So we can only intersect 2h with h and h. So this equal to 0, this is equal to 0, this is equal to 0. So h cubed is equal to a half, which means that an x has degree 2, so as a divisor this has to be 4h. You can check this explicitly. At home you can check that if we intersect, like we have coordinates x0, x1, x2, x3. You can check at home if you intersect x0 equal to 0, x1 equal to 0, and x2 equal to 0, we get the singular point. And you can check if you intersect x3 equal to 0 and x0 equals x1 equal to 0, then we get a non-singular point. 1 point, exactly 1 point. So that's why hash cubed is equal to a half. Now we can do the last case. How can we do this case? Не понимаю, можно...
I think the same thing.
Okay.
However, we also need R3 to generate.
So yes. So it's generated by r less than or equal to 3. And before we start, it's useful if we write down the dimension of I when, say, I is equal to 1, 2, 3, 4. What do we get here? So now we're doing the case x squared is equal to 1.
Ну да. По формуле такой, да. m равна единице, как квадрат равна единице.
Aha, 2, then
4.
yes, then
Plus 7.
yes, and finally yes. Okay, then the anti-canonical linear system gives what kind of a map? So the anti-canonical linear system is not free anymore. Yes, but it will be birational. And if you want the geometric picture, it's because X is the blow-up of P2 and 8 points, and the anti-canonical linear system is the family of cubic curves passing through those 8 points. So this map is not defined on the 9th point of this family, but it's defined.
Здесь одна базисная точка. Помните, мы объясняли, что все кривых через одну точку проходят. Вот в этой точке это отображение не определено, естественно. Во всех остальных точках это отображение определено правильно.
Minus 2kx, we know that this is free already. So this gives an actual morphism into what? Da. What would be the image of this map? What? Yes. Why?
Ну, особый конус точка. Но степень 2 и еще
Ага.
одна базисная точка.
The degree is 2, so yes, so it has to be, the image is a cone, and what is the degree of the morphism? So let's call it f of x has degree equal to what? 2, but why?
Понятно, как пересекаются вот, элементы отсюда друг с другом? По скольким точкам пересекаются? Какова степень вот отсюда? По 4 точкам, совершенно верно. Значит, они пересекаются по 4 точкам. Значит, тотальная степень вот этого сюда 4. Значит, если мы попадаем куда? Мы попадаем куда? Мы договорились уже, когда мы попадаем? А? Но это не является вложением, да? Значит, мы попадаем куда-то... Какие могут быть варианты? Мы попадаем куда-то степени 1, например, на плоскость, да? Но можем ли мы попасть на плоскость степени 1? Не можем. Почему? Потому что тогда было бы пространство меньшей размерности. А у нас здесь очевидно, что мы не можем попасть под пространство меньшей размерности, потому что это полная линия системы. Вот, значит, мы попадаем либо в степень 4, и тогда это вложение. Но этого не может быть, потому что мы знаем, что это не вложение. Значит, мы пытаем на степени 2 и на третьей степени 2. Тотальная степень 4.
So how are we sure that the map doesn't have degree 1 and the image has degree 4?
This is not an embedding.
It could just be some resolution of singularities. So the image it can't have degree 1 for sure, because then it would be contained in here. So it either has degree 4 or it has degree 1. That's exactly the answer. It has degree 2, the image has degree 2, but why? How are we sure that the degree of the map is not 1 and the image has degree 4?
Because there are no curves which intersects
What?
There are no contracted curves yet. And it's degree 1.
I say that again. So if it had degree 4, then...
Yes, because математика класса 1, поэтому не стягивается. И когда не стягивается,
If some curve
это физика конечна.
compress, then it has negative intersection.
So if it had degree 4, then it would be x some k3 surface. In this map, if it would...
Too complicated. Нет, это вложение, потому что эта система обильная, понимаешь, в чем дело? Если бы это было в степени 1, то это не могло ничего стянуть, оно не может ничего стянуть. Оно base point free.
Да.
Base point free, поэтому это настоящее отображение. Стянуть оно ничего не может.
Хорошо.
Обильное. Не надо как 3 поверхности нам сейчас.
Хорошо.
Это намного проще, да.
Хорошо, все ясно. So the image has degree 2. Okay. Now we can do all the computations. So what will S1 be?
What is S1? S1 is number?
Yes.
Okay.
Wait, what? Yes. Can we find out S2? So to find out S2, we need to find out what is the image of the dimension of the image of symmetric square of S1 to S2. How can we find the dimension of this image?
Опять вложение?
We can just look at this.
Embedding is embed 3.
No, this is not an embedding.
Здесь два сечения.
Нет.
Вот, 1 и 2. И все туда входится 1 в квадрате, 2 в квадрате, 1 в 2.
Да.
Еще одно.
Здесь не S1, а R1.
Да, спасибо.
Еще одно.
And why doesn't any of these vanish on X? Okay, it doesn't, because this is a dominant morphism.
Сколько не хватает?
Одного.
Okay. Then we just need to compute S3. That's the last thing we need to compute. So we need to compute the dimension of the image of R1 tensor by R2 inside R3, inside here. Почему это счастье?
1 в кубе, 2 в кубе. 1 в кубе, 2 в кубе, 1.
Хорошо, but how are we sure that none of them vanish on X? So I... No, not necessarily. So I agree that the map of degree 3 gives an embedding of X inside P6. That's fine. But this tensor product, we have a map birational map from X to P1. Then we have a map from X to P3, and then we obtain a map from X to the direct product, birational at least, times P3 and we embed it inside P7. And x will be contained in some number of hyperplanes here, but it's not clear to me that these A1, that something like here we've added say B, that B times A1 restricted to x is not 0. We have some map here. We basically, geometrically, we need to find out how many hyperplanes here contains x. But as far as I can see, when we're taking the tensor product, some of these sections, when we restrict it to x, could vanish. Like we have some complicated geometry here. This is degree 2. This is a vibration of genus 1 curves, and then we embed it into the direct product. I don't think this map is an embedding of x, it's just birational. So we need to show that the image here, the answer is 6. So we need one more element, so the answer is correct. But to show that, we need to show that the image of x inside here is not contained in some 5-dimensional linear subspace, some 4-dimensional linear subspace. If the image here was contained inside some 4-dimensional linear subspace, then we would be in trouble. So here,
We have conclusion to before that we have some linear system which define this conclusion.
yes, and it would just exactly be the image here inside R3. So the image of R1 tensor R2 inside R3, that's the linear system. That linear system defines the birational map from x to P7. How are we sure that this image isn't contained in some 4-dimensional linear subspace? A priori, that's possible. If some of, in this tensor product, if the image here is 5-dimensional, if some of them, if B times A1 minus A2,
Can't we just say that we have this map and then we have some device which define this map and have some contradiction because we don't have this device actually?
Nie poнял.
Okay.
So, I think we need here to be more clever and look at actually look at R4. So what can we say about the dimension of the image of symmetric square of R2 inside R4? What is the dimension of this image here? It's the linear system of conics here, such that when we restrict it to x, it doesn't vanish. So R2, it's the same as H0 on P4 of O1 restricted to x. When we restrict it to x, it gives an isomorphism between this vector space and R2. Then when we take the symmetric square, we obtain the symmetric square of this vector space, which is global sections of O2. And we need to find the dimension of the vector space of conics in P3, which doesn't, such that when we restrict it to x, it doesn't vanish. So we have this whole map. We have H, we have R1, P3,
Where did you find it?
What?
Where did you find it?
This argument,
Yes.
Nick,
Too complicated for me.
I think there's, do you have another argument?
Yes, it's much easier should be.
What's your argument?
What is the problem with explicitly writing down all the combinations of generators of S1 and S2?
Because when we restrict it to x, they could vanish.
Shouldn't there be some kind of
is, look, let us consider the tensor product of kx to O minus 2kx. It goes to the O minus 3kx, yes? Such map. And this map induces, let us consider the section of this guy. It's a two-dimensional vector space, yes? So we have a map from H0 of x, so minus kx. That is two-dimensional. And the O minus 2kx, it goes to the O minus 3kx. Let us look on the kernel and co-kernel of this map. What is co-kernel of this map? So it's two-dimensional vector space. It's two-dimensional vector space. It's two-dimensional vector bundle, so it's direct sum of this guy 2 times. Yes, this is exactly the O minus 2kx 2 times. That just goes here. Okay?
What?
It's two-dimensional vector space.
Yes, yes.
So this means that this map. Look, what is a kernel and co-kernel of this map? What is a kernel and what is co-kernel? What is a co-kernel here? It's just a structure shape of the base point. So we have base point of minus kx. So we know minus kx has one base point that is goes here.
Wait. Why is the co-kernel LP? I didn't understand.
Because what is actually, so co-kernel is where all these maps are zeros, so where it's exactly, okay?
Okay. But how are we sure that we have
What is a kernel?
How are we sure that we have only one base point? We haven't proven that.
One base point?
Why?
No, we know it.
Why?
We just consider the, I explained before.
Yeah, but
just we consider the restriction of minus kx on the C. It has only one base point there, just the intersection of this. It's evident.
Okay.
So it's just a base point. What is a kernel here? It's exactly O minus kx here, just because it's a so I mean that just because it's 2 times minus 2kx, so we have just значит, у нас есть линейное расслоение 3kx, у нас есть два линейных расслоения 2kx, значит 2 плюс 2 4, минус 3, получается 1. Здесь стоит минус kx. Вот, получаем такую точную последовательность. Дальше смотрим на когомологии. Когомологии вот здесь, это в точности R1 тензорно на R2 имеет размерность 8. Вот это имеет размерность 2. Вот здесь 2 вкладывается в 8, вот здесь получается 6, плюс еще вот одно отсюда. То есть здесь на самом деле мы знаем, что размерность вот это 7. Значит, вот это вот отображение в R3, собственно говоря, получается образ, это вот это шестимерное пространство. Понятно, 8 минус 2, вот это в ядре стоит двумерное, вот это шестимерное получается, который сюда вкладывается. Остается семимер только единичка, все, больше ничего здесь не остается. То есть это совершенно простая вещь. А это все не нужно.
Ладно.
Ну и по-простому вы должны просто для себя понять, что здесь получилось. Значит, у вас что есть? У вас есть вот эти элементы, значит, у вас есть А1 в кубе, А1 в квадрате, А2, А1, А2 в квадрате, А2 в кубе, и есть еще b умножить на А1 и b умножить на А2. Собственно, вот это и есть базис того шестимерного пространства, которое получается. Ну, то, что вот он базис, вот более-менее я их показал, потому что это 8 минус 2, там, вы смотрите, что оказывается. Ну вот и все, значит, то есть вот эти 6. Ну и одного еще не хватает, который надо добавить.
Да. Much simpler.
Да.
So, the del Pezzo is embedded into weighted projective space, how many ones?
Один, два, три.
Да. N,
Шесть.
почему? So, hash кубик равно.
Одна шестая.
А?
Одна шестая.
Да.
Ну, потому что на самом деле общую формулу, то есть если величина пространства А1, А2 и так далее, АН, то его n плюс первая степень, n-тая степень, будет единица разделить на А1, А2 и так далее.
Да. Все?
Все, да? Давайте только вот я сейчас вам вот это вот немножко объясню. Значит, вот здесь получилось 4. Давайте еще раз глянем это с другой стороны. Просто помните, я сказал, что у нас есть на самом деле отображение в P2. То есть у нас вот это x отображается в P2. И это двулистное накрытие. Вот как это связано с тем, что это вот здесь. Давайте посмотрим. Значит, у нас здесь, ну вот как бы у нас переменные x0, x1, скажем, x2 степени 1. И еще есть переменная y, которая степени 2. Да? Как записывается уравнение четвертой степени в этих переменных? Давайте, как оно будет выглядеть? Это будет y в квадрате, y степени 2, поэтому 4, y квадрат будет иметь степень 4, да? Y в квадрате плюс какой-то многочлен от x, f от иксов, значит, на y, плюс какой-то многочлен g от иксов. Значит, многочлен f какой степени? Второй, да. Значит, а многочлен это четвертой степени. Вот. Ну и, соответственно, ну, условно говоря, вот это может вот это исключить, привести, ну, как обычно квадратное уравнение, можно так скажем исключить. Но просто вы должны понять, что вот, собственно говоря, вот эти иксы, это образует вот эту P2. А вот это y в квадрате дает, собственно говоря, что у нас вот это двулистное отображение. То есть, если мы иксы подставили, то сколько у нас вариантов для y? Ну, 2 квадратных уравнения мы должны решить, у нас получится 2 варианта для y. Это и есть вот это вот двулистное накрытие. А в чем оно разветвлено? Оно разветвлено тогда, когда, соответственно, у нас, соответственно, здесь только y имеет один корень, да, то есть надо дискриминант посчитать. Ну, дискриминант, значит, это в квадрате минус это, то есть дискриминант, когда вы считаете, это многочлен четвертой степени от иксов, то есть все это разветвлено на кривой степени 4. То есть у нас получается такая вот плоскость, двулистное накрытие над этой плоскостью, то есть над каждой точкой у нас это. А в каких-то точках у нас, ну вот как двулистное накрытие, имеет ветвление, да? И это ветвление вдоль кривой степени 4, соответственно, получается. Понятно? Вот. Ну это вот описание, соответственно, вложено, оно степенью 4 в это P1, 1, 2. Ладно, это вот. Спасибо. Какие-то вопросы есть к Алексу? Спрашивайте. По-английски.
Не можно по-русски.
Can we get classification of the Pezzo surfaces so it's on another part of
You mean that if it's algebraically closed field and characteristic 0, then it's yes. So this is all based on Color's geometry of algebraic curves, and then after this, they uses this to conclude that actually it's just he puts it as an exercise to prove that that is the only cases over a closed field in characteristic 0. So yes, it's useful. At least it's useful that the anti-canonical linear system is very ample in the remaining cases.
Yeah, it's just
So I mean, this theorem here is important.
Нет, просто что у нас есть классификация, ну, классификационная теорема, и это какой-то шаг на этой классификационной теореме, или это вообще в другую сторону какая-то?
So this part for sure. And you can also try to show that then, for instance,
Ну, на самом деле, я не знаю, просто вы знаете или нет, что, ну, понятно, что над комплексными числами, например, значит, над корень характеристики 0 и алгебраически замкнутым, все дель Пеццо описывается следующим образом. Но у нас есть P2, это дель Пеццо с какой степени, вот с точки зрения, вот степени мы тут в квадрате писали?
9. А.
9. Почему? Потому что канонический класс это минус 3h, в квадрат надо возвести, получится 9 на квадрате, это равно единице, это 9. Значит, собственно говоря, степени бывают 9, 8, 7, 6, 5, 4. Здесь вот в обратную сторону, но я пишу это 4, 3, 2, 1. Вот. Но, значит, вот P2 это степени 9, оно одно. В степени 8 у нас есть следующее. У нас есть P1 на P1. Это произведение P1 на P1. Либо раздутие P2 в одной точке. Ну, часто пишут поверхность F1. Это, я не знаю, но это надо знать, что такое раздутие. Берете эту точку и одну кривую раздуваете, получается минус 1 кривая здесь вклеивается. Вот. А все остальные можно получить просто. Это раздутие P2 в 2 точках, это в 3 точках, это в 4 точках, это в 5, в 6, в 7 и в 8. Только точки должны быть в довольно, в достаточно общем положении. То есть вы можете выяснить, что это значит общее положение. Ну, это я сейчас не буду объяснять. Но, в общем, то есть вот, и более того, если вы берете, там, скажем, 8 точек в достаточно общем положении, можно сказать, что это значит общее положение, вот, и вы их раздуете, то вы получите дель Пеццо степени 1. То есть вот с точки зрения алгебраической геометрии напольно комплексных чисел, вот в этих терминах все намного проще описать, чем вот в тех терминах. Ну, понятно, что если у вас поле не алгебраически замкнутое, то у вас уже могут быть здесь варианты, потому что группа Була начинает действовать, она может минус 1 кривые переставлять и прочее, прочее. Вот. А это вот просто вот вся полное описание поверхностей дель Пеццо, соответственно, над полем комплексных чисел.
Можно как-то легко понять, что степени больше 9 не бывает?
Можно ли как-то легко понять, что степени больше 9 не бывает?
Это можно реально вычислить. На самом деле там можно использовать, как раз значит, надо раздувать точкой, чтобы они были в общем положении.
Нет, это уже если вы... Нет, раздувать... Нет, все, когда ты раздуваешь, все только уменьшается.
So, and this holds an arbitrary characteristic. So you can show that if the pk rank is 1, then it has to be isomorphic to P2, no matter the characteristic, as long as it's algebraically closed.
Ну, это в теории поверхностей, естественно, доказывается, но это все-таки некоторое утверждение, это теорема некоторое, что больше 9 не бывает. Но там некоторые числа между собой связаны.
Там есть формула про ранг связан, это 10 равняется ранг плюс... Да, что-то такое.
А если мы не в общем положении раздуваем, то просто...
Ну, в общем положении, вот самое необщее положение начинается когда? Когда у вас, вот, например, вы раздуваете 3 точки на плоскости. Какое необщее положение? Ну, 2 точки, они, если они не совпадают, они всегда в общем положении. Когда 3 точки не в общем положении. Да, совершенно верно, когда они получатся на прямой. Ну и что здесь произойдет? Вот в этом случае вы уже получите не поверхность дель Пеццо, а что произойдет? Что будет мешать ей быть поверхностью дель Пеццо? Вот собственный прообраз вот этой вот, собственно, прямой. Вы на ней раздули 3 точки, и дальше, если вы посмотрите, как она теперь пересекается с каноническим классом. Вот взяли эту кривую, то есть вот у вас здесь вклеились минус 1 кривые, соответственно, у вас как класс можете посмотреть, и теперь ограничить ее вот на эту, собственно, прообраз, на эту кривую. Вы получите, что канонический класс, пересеченный с этой вот кривой, у вас получится равен нулю. Это и будет как раз противоречить тому, что это канонический класс у вас один. То есть отображение с помощью канонического класса будет эту кривую стягивать в особую точку, на самом деле, в конус, на самом деле. То есть вы вот пойдете во что-то, вот в такой конус вот пойдете, вот в эту точку, это минус c тянется. Вот это не общее положение. Дальше, когда много точек раздувается, там бывают более сложные. Там, например, нужно смотреть, чтобы там 6 точек не попало на коник, например, там, ну вот какие-то вот такие вещи. А дальше еще более. Еще вопросы? Ну, если нет, давайте еще раз Алекса поблагодарим.